Hello, and thank you for stopping by helpyourmath.com. In this video, we're going to look at some examples of linear factorization of polynomial functions. And just to clarify, when we're asking for the linear factorization, that means each factor should be a linear factor. So if we have k of x, each factor would be like root 1, x minus root 2. What we shouldn't see is something like x squared minus root 3, because this would not be a linear factor, that would be a quadratic factor. So we'd have to take that one a step further to figure out what the linear factors actually are. So when we write it out, we want to make sure that this just has x and not x squared. This just has x and not x squared. It's okay if there's an exponent here, because the factor itself is still linear. In our first example, we're given g of x. We want to list all possible rational zeros, use synthetic division to show that -4 is a root, find the remaining zeros of g, and then the complete linear factorization. So to find the list of all possible rational zeros, that's the rational zero test. And the list of possible rational zeros is determined by taking the, hold on, almost there. Okay. It's by taking the factors of the constant. So in this case, the constant is 36. So we're going to look at the factors of 36 and divide them by the factors of the leading coefficient, which is positive 1. When we talk about factors, this includes negative factors. And we only consider when the numerator and the denominator, the factors of 36 and the factors of 1, have a GCF of 1. If they have a GCF other than 1, then we don't have to worry about it because it's already included in the list. So the factors of 36, and again, we include the plus or minus, that would be plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. And the factors of 1 will be plus or minus, oh, I don't need to say -1 or 1 because I would just say 1. So there's two factors of 1, 1 and -1. We don't really have to worry about the 1 and -1 because we're going to include all of them when we use that positive or negative sign. And basically dividing anything by 1 is just going to it's just going to be the numerator. So the list of possible rational zeros, we're going to put our positive or negative right here and just say 1, 2, 3, 4, 6, 9, 12, 18, and 36. And that's it. Well, not that's it, because that's a lot of factors, but those are the only possible rational factors. The complete list is right here. So that's nice because all of the possible rational zeros are also integers. Okay, in letter B, we're going to use synthetic division to show that -4 is a root. So to set up synthetic division, we put -4 outside our upside down division, and then we write the coefficients in constants. That would be 1, 4, 9, and 36. Bring down the 1, multiply -4 to 1, add, multiply, add, multiply. We have this remainder of 0. That's what demonstrates to us that -4 is in fact a root. That's how we know, because the remainder is 0. Okay, so that was part B. Part C, find the remaining zeros of g. So we know one zero is -4 because it was given to us. The remaining zeros of g, we're going to use these as our coefficients and constants of the other factor besides x plus 4. That would be x squared, because it gets reduced by 1 degree. There's no x, and then it would be plus 9. So basically what we're looking at here, I'm just going to put the whole thing, this would be x plus 4 equals g of x. So g of x is partially factored now, but we still are supposed to be finding the zeros and writing the complete linear factorization. I know that what I just wrote is not linear, because the x squared is not a linear term. So to find the remaining zeros, we're going to take the other factor, this one, and set it equal to 0. If I want to, I can subtract 9 from both sides. That would give me x squared equals -9. And then take the square root of both sides. When I take the square root of the numerical side, I do include that plus or minus. The square root of -9 is 3i. So I would end up with, plus or minus 3i. So those are the other two zeros. So we can just list the zeros. We'll just list all 3 of them. And 3 is the maximum number of zeros because the degree was 3. So we've maxed out the zeros. We have -4, -3i, and 3i. So that would be our answer for letter C. And then for letter D, the complete linear factorization. So again, I'm going to take each zero and write it as its own factor. That would be x plus 4. And make sure and notice that I'm writing x plus 4 The 0 was -4. When you put it back in the parentheses, it's like the opposite, right? Because you have to set that thing equal to 0. That's why it ends up looking like it's the opposite. And then if we're going to turn that into a factor, that would be x plus 3i. And if we're going to turn this into a factor, it would be x minus 3i. So we have our 3 factors, which is what we should have. We should have exactly 3 factors, and we do, and every factor has a degree of 1. Here we're looking at h of x, and we're going to do the same thing. So the possible rational zeros, that would be the factors of 30 divided by the factors of 2. And the factors of 30 include plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. And the complete set of factors of 2 are 1 and positive and negative 1 and 2. So when we look at this list, that would be 1 divided by 1. Oops, wait, I forgot my plus or minus. Don't want to forget the plus or minus. That's kind of important. That would be 1. Then we could do 1 over 2. Then 2 over 1. 2 over 2 we don't include because that's a GCF other than 2. 3 over 1. 3 over 2. 5 over 1. 5 over 2. 6 over 1. 6 over 2 we don't worry about. 10 over 1. 10 over 2 we don't worry about since 2 and 10 have a common factor besides 1. 15. 15 over 2. And lastly, 30. We don't include 30 over 2 since 30 and 2 have a common factor. So here's our complete list. Positive and negative 1, positive and negative 1/2, and down the line it goes. So we have a lot of possible rational zeros here, including some fractions. B, we're going to show that 3/2 is a root. And let's consult. Hey, look, it's on the list. Okay, good. So we're going to use synthetic division to show that 3 over 2 is a root of this function. We're going to list, we have 2, 1, negative 16, negative 5, and 30. And for this one, since it is a degree 4 polynomial, we are expecting 4 zeros. Bring down the 2, multiply, 3/2 times 2 is 3. 1 plus 3 is 4. Multiply, 3/2 times 4 is 6. And that would be negative 10 when we add. This would be negative 15. This would be negative 20 when we add. When we multiply here, this is negative 30. And there's that 0 that we're looking for. So that confirms that 3/2 is in fact one of the zeros. Now we want to find the remaining zeros of h. So we know we have h of x. We know one synthetic division. We have one factor, which will be x minus 3 over 2. And what it's getting multiplied to would be 2x cubed plus 4x squared minus 10x minus 20. From here, we're trying to find the remaining zeros, so we're going to take that second polynomial, that second factor, and set it equal to 0. If we can't factor this, then ultimately we would have to go back to the list of possible rational zeros and see if there's another rational zero. Luckily, I do think this is factorable. There's 4 terms, so we can check factoring by grouping. And when we pull out the GCF here, we get 2x squared, leaving me with x plus 2. Here we're going to factor out a negative 10, leaving me with x plus 2. Those 2 terms do in fact have a GCF. They have a GCF of x plus 2. That would be x plus 2 times 2x squared minus 10. We're going to set each factor equal to 0. If x plus 2 is equal to 0, that means that x equals negative 2. If 2x squared minus 10 equals 0, then 2x squared equals 10, and x squared equals 5. Take the square root of both sides, and we get x is equal to positive or negative square root of 5. So just to list out the zeros, although I am running out of room, I'm going to do it right up here. All of the zeros are x equals, and what do we have? We have negative 2, 3 over 2, negative root 5, and positive root 5. Those would be our 4 zeros. This was a degree 4, so 4 zeros is to be expected. And lastly, letter D. Now we're going to take those zeros and just plug them back in to factors of this polynomial. So this would be h of x equals, we have x minus 3 over 2, x plus 2, x minus root 5, and if I can squeeze it in, x plus root 5. So 4 factors, which is what I should have for this particular polynomial. In our last example, we're given f, and we're going to do the same thing. So first, listing those possible rational zeros. That would be plus or minus the factors of negative 15, which would be 1, 3, 5, and 15. And dividing those by the factors of 4, 1, 2, and 4. So that's going to give us positive or negative. That would be 1 over 1, 1 over 2, 1 over 4, 3 over 1, 3 over 2, 3 over 4, 5 over 1, 5 over 2, 5 over 4, 15 over 1, 15 over 2, and 15 over 4. So we ended up not having any duplicates there. Everything ended up working out. So that's the list of possible rational zeros. Next, we're going to use synthetic division to show that 3 is a root. So we're going to list this out. We have 4, negative 27, 61, negative 43, and negative 15. Bring down the 4. That would be 4 multiply, that's 12. Add, that's negative 15. Multiply, negative 45. Add 16. Multiply 48. Add 5. Multiply 15. And 0, which is what we expected. Okay, so next we're going to find the remaining zeros. So we're going to take what's left here, 4x cubed minus 15x squared plus 16x plus 5 equals 0. And unfortunately, this is a degree 3 polynomial, and we can't use factoring by grouping. If I group the first grouping and second grouping won't have a common factor. So what we have to do is we have to go back and check with a bunch of synthetic division to see if we can find another rational root. And you can start this however your heart desires, whatever makes the most sense. So you can start with, let's say, just going down the board, we can try 1 and see if 1 works. We're going to plug 1 into what we just wrote in C. So we're going to use 4, negative 15, 16, 5. We bring down the 4, 4, negative 11. That's negative 11. 5. Oh, it looks so good, but that is a remainder of 10. So that means that 1 is not a rational zero of this function. Then we would try something else. You could try negative 1 and see if negative 1 works, because we were so close with 1, maybe it's negative 1. So 4, negative 15, 16, 5. That would be 4, negative 19, 19. This one's looking really bad. 35, negative 35. That's not going to work. That's going to give us a remainder. So we have to play this game with all of these possible rational zeros and hope that we find another one. And we should find another one, because there should be one other zero that exists. And just for time's sake, I'm going to go ahead and tell you that it is negative 1/4. So if we check negative 1/4, because we're going to need that quadratic, this would be 4, 27, I'm sorry, looking at the wrong coefficients. Let's try this again. 4, negative 15, 16, and 5. We bring down the 4. This would be negative 1, negative 16, positive 4, 20, negative 5, and we found that 0. So unfortunately, it might have taken a little bit of time to finally actually check that negative 1/4. Luckily, I knew the answer, so whew, that saved us. All right, so we have another 0. We need to find the remaining zeros, so we're going to write this as our quadratic. We're going to say 0 equals 4x squared minus 16x plus 20. To start this off, I'm going to divide everything by 4 just to make the coefficients and the constants smaller. Dividing 0 by 4 will keep it 0. That's going to give me x squared minus 4x plus 5. Now looking at this, it almost looks like it should be factorable, but unfortunately, it's not. So if it's not factorable, we're going to have to use either the quadratic formula or completing the square. Whatever your preference is totally fine. Maybe I'll do completing the square, because I almost never use completing the square. So for completing the square, we're going to get this by itself. So I'm going to subtract 5 from both sides. And then what would be the third piece to make this a perfect square trinomial? Well, we would divide negative 4 in half, which would be negative 2, and square it, which would be positive 4. So then I'm going to add 4 to both sides. That would give me negative 1 equals, and then this would become x minus 2 squared. Now to get the square off the x, we'll take the square root of both sides. I see we're going into imaginary numbers here. Woo! This one's taking up a lot of space. The square root of negative 1 is I, so that's plus or minus I. And then over here we have x minus 2. Lastly, to get x by itself, we would add 2 to both sides. That'd be 2 plus or minus I equals x. So there are the remaining zeros. So to write all of the zeros out, we would have x equals, and what we have? We were given 3. We found, we found negative 1/4. And then we found 2 minus I and 2 plus I. So we should have had a maximum of 4, and we do in fact have 4 zeros. Lastly, we want to write the complete linear factorization. So that would look like, so I'm going to go up here just because I pretty much dominated the rest of this. Stop it. And we're going to have x minus 3, x plus 1/4, x minus 2 plus I, and x minus 2 minus I. And that would be our complete linear factorization. And actually, one note about this final answer. This actually is not the final answer. Remember over here, where'd it go? Right here, where I divided everything by 4? Well, I needed that 4. That 4 was actually part of this function. So what I'm going to do, since I divided by 4, I'm going to put that 4 out in front. That way the 4 still exists. Because if we see we have a leading coefficient of 4, and here, if we were to just multiply, we would only have a leading coefficient of 1. So we need to put that 4 in front. You could also take the 4 and multiply it to this factor, which would give you 4x plus 1. And that way you don't have any fractions in your factors. That's really up to you.